Welcome to this brief presentation on inverse Laplace transforms using standard forms. Okay, in this presentation we're going to start by defining the inverse Laplace transforms. We're going to review the inverse Laplace transform table of standard forms, which you must be very familiar with. We need to look at some worked examples on using the standard forms, and there'll be some tutorial exercises on using standard forms for you to do. Then we'll look at examples of taking our functions and resolving them into simple partial fractions and then into standard forms. And then we'll look at examples of completing the square on functions given and then into standard forms. And there'll be some exercises and questions to leave you with at the end. Okay, this slide will just briefly outline the definition of an inverse Laplace transform. If we consider the Laplace transform of a function of t from our Laplace transform tables, we can find its appropriate function of s, going from the time domain to the s domain. So we can actually reverse this process and call the function of t the inverse Laplace transform of the function of s. In other words, function of t is equal to the inverse Laplace transform, notice notation there, of the function of s. So for example, if we start with the Laplace transform of k, we know from Laplace transform tables that is k upon s in the s domain. If we were to reverse this process and find the inverse Laplace transform of k upon s, we would get back to k in the time domain. Similarly, if we take an example of Laplace transform of sine at, we know from the Laplace transform tables that's written as a upon s squared plus a squared in the Laplace domain. If we reverse this process by finding the inverse Laplace transform of a upon s squared plus a squared, we get back to sine at in the time domain. So this is what we mean by taking inverse Laplace transforms. We are going from the Laplace domain, the s domain, back into the time domain. Here's shown a standard inverse Laplace transform table, part of the table here, and we need to get quite familiar with the formats in the table, and the more you engage with this work, the more familiar you will get with these formats. So this is the inverse Laplace transform table. So on the left hand column here I have the Laplace transform of the function of t, and on the right hand column here I have the inverse Laplace transform to get us back into the time domain of function of t. So for example, if we take 1 upon s as being our Laplace transform, the inverse function, the inverse Laplace transform function is 1, so 1 in the time domain. If our Laplace transform is k upon s, then our inverse Laplace transform will give us k. If it's 1 upon s minus a, that goes to an exponential function e to the at in the time domain. 1 upon s plus a goes to e to the minus at in the time domain. The Laplace transform of a over s squared plus a squared goes to sine at in the time domain, and s over s squared plus a squared goes to cos at in the time domain. And we need to get familiar with the functions that have, for example, a linear s in them, or the functions that have an s squared in them. We need to start to get familiar with that. The more familiarity we can have with the table, the easier we'll find, and the quicker we'll find we can undertake the inverse Laplace transforms. The table continues here, same thing here. We've got our Laplace transform on the left hand side and our inverse Laplace function of t on the right hand side. So 1 upon s squared goes to t in the time domain. Laplace transform of 2 factorial over s cubed is t squared in time domain. N factorial over s to the n plus 1 goes to t to the n in time domain. A upon s squared minus a squared is a sine function, sine at in time domain. S upon s squared minus a is a cosh function, cosh at in the time domain as hyperbolic functions there. Factorial n factorial over s minus a to the n plus 1 goes to e to the at times by t to the n in time domain, and then we've got some exponential and sine and cosine functions here. So omega over s minus a squared or squared plus omega squared goes to e to the at sine omega t. S minus a over s minus a squared plus omega squared goes to e to the at cos omega t. And then we've got here sine functions and cos functions. So omega over s minus a all squared minus omega squared goes to e to the at sine omega t. And then finally we've got s minus a over s minus a all squared, take away omega squared goes to e to the at cos omega t. So we need to get quite familiar with these inverse Laplace transforms. It will help us in our understanding of the process. Okay, going to look at the inverse Laplace transforms here of some simple functions. Example 1 has 3 parts to it. Going to look at part A first of all. So we're looking at the inverse Laplace transform of 1 over s squared plus 9. That's the function we're given. Now straight away from my knowledge of the tables on the previous pages, I know that there's a function in the denominator that has an s squared and an a squared in it. So I could actually write the 9 as 3 squared. Because I know that the denominator of s squared plus a squared is in the table, and here it is. I've actually extracted this from the previous table. So if I could get the function we were given in the form of a over s squared plus a squared, I could simply write the answer down as the sine at. So to do that, what we're going to do here is replace this 1 here with a 3, because if I'm going to comply with the Laplace transform here, I have to have the a over the a squared term. So I need a 3 on the top. But of course there's really a 1 on the top, not a 3. So I've changed the sum if I add the 3 to the numerator. But if I add a 3 outside here to the denominator, then of course the 3 divided by 3 cancels to give me 1 again. So I haven't affected the original question given to me. So I can write the 3 over s squared plus 3 squared straight away down as sine of 3t, because the a in this case would be 3. But I mustn't forget in this case to divide by the 3, which is outside of the inverse Laplace transform function. But this is the way we try and approach Laplace transforms, try to make them into standard forms using this kind of manipulation process. And you'll see more of that as the examples unfold. Okay, looking at example 1 part B this time, I'm asked to find the inverse Laplace transform of 5 divided by 3s minus 1. Now again, we need to kind of think through the sort of format we're looking at here. We've got an s term on the bottom line in the denominator, so that eliminates the s squared terms in the table. And if I look at my table, I will see something like 1 upon s minus a in my inverse Laplace transform table. If I was to take the 5 outside, because don't forget the 5 is a factor, just factoring up the function here, I can keep a 1 then on the numerator over the 3s minus 1. And again, I'm sort of looking more similar to the 1 upon s minus a function. Little technique we use here to get the s on its own is to divide each of the terms in the numerator and denominator by 3. This will then allow us to have an s function, not a 3s function on the bottom line. So in other words, we're going to take the 1 and divide it by 3 on the top line, so that can be 1 upon 3. If we take the 3s and divide it by 3, we will get 1s or s. And if we take the 1 again, divide it by 3, we will get the minus 1/3. I'm still not quite in the format of 1 upon s minus a. I have my s and I have my minus a, you could say, on the bottom line, but I have the third on the top. So again, we can take out the constant of the third, which we're dividing by here to 1 upon 3, so that comes on the denominator outside, so I have 5 upon 3 outside the inverse Laplace transform function, and now that's left me with 1 upon s minus 1/3 inside the bracket. So again, looking at that, I've got my standard form of 1 upon s minus a, where the a in this case will be the 1/3. I now write that in terms of the function, so that will be e to the t upon 3, so the 1 upon s minus 1/3 is written as e to t upon 3 from the inverse Laplace transform table, and don't forget I have to multiply by the 5 and divide by the 3 in this case. Example 1, part C here. The inverse Laplace transform we're asked to review this time is 2s over s squared plus 5. And again, I need to think to myself from the tables, there are terms with s in the bottom, there are terms with s squared in the bottom, so I need to look at a term which has an s squared in the bottom. I also need to be aware that there's an s on the top of this function. So if I take the 2 outside as a constant factor, 2 is outside the inverse Laplace function, that would leave me with s upon s squared plus 5 inside the function. Now if I look at my Laplace transform table, there's a function that's quite similar, s upon s squared plus a squared, looks quite similar to the s upon s squared plus 5 in my case. And again, a little a technique we use here to make it into the form of s squared plus a squared in the denominator is we square root the 5 and then add the squared to it. So in other words, I'm not changing the original function because the square root of 5 all squared is 5, and that's the original term in the function. But I've written it now into the form of an a squared, where my a would be the square root of 5. So I've ended up with 2 outside of the inverse Laplace function of s over s squared plus an a squared, where the a squared is square root of 5. So in my solution here, the cos of at will be the cos of the square root of 5, which is the a here, times by the t, okay, inside the cos function, and then I multiply the whole function by the 2. Okay, exercise 1 shown here. There are 4 different little questions to try here in this exercise. The answers are shown in the square brackets below. Just some hints for you. For part A, you will be looking for, I would suggest, something that has an s minus a in the denominator. For part B, you'll be looking for the function that has an s plus a in the denominator. Part C, looking for something that has an s only in the denominator, and then in part D here, looking for something that probably has an s squared plus an a squared type of function in the denominator. So that's what sort of gives you an indication of the inverse Laplace transforms to use. Same with exercise 2, try and look at the denominators, see if they give you an indication. I would suggest you're looking for part A at something that has an s squared plus a squared, but with an s on the top. Not a constant on the top, but an s on the top. In part B, you've got something that has a sort of s to the n type function, I would suggest, and the same with part C, looking for an s to the n type something with constants on the top here. Part D, this is a slightly different format here. I would suggest we're looking at something that has the s minus a all squared plus an omega squared type of function here. I'll let you have a look in detail of those, but those would be the kind of things that I would be considering in each of those functions. Okay, moving on to example 2 here. Just show you a variation. We're still using standard Laplace transforms here, but a slight variation in the approach here. We're asked to find the inverse Laplace transform of 5s plus 8 over s squared plus 16. Now there'll be no function in our table where we have an s plus an a on the top line. If you scan through the function in the previous part of this presentation, you won't see a sort of an s plus a on the top line. So one of the techniques we can use is to resolve this function into its partial fractions. So in this case, given the inverse Laplace transform of 5s plus 8 over the s squared plus 4 squared. Notice I've put the 16 into 4 squared because often it's an a squared term on the bottom, so I've changed the 16 to 4 squared. What I could do is write these Laplace transforms, the inverse Laplace transforms, in terms of the partial fractions. So I'm just going to take the 5s term and write it over s squared plus 4 squared, and then I'm going to add to that the inverse Laplace transform of the constant 8 over the s squared plus 4 squared term. So by doing that, I make it these into more like standard forms that are in our table, and something I can kind of break down to smaller chunks to deal with. If you look in the table of inverse Laplace transforms, you'll see an a upon the s squared plus a squared type of function, which tendency to be looks like the latter term, latter partial fraction, and we've got an s over s squared plus a squared term here, which looks a bit more like the first partial fraction above. So I've now got a handle on how I can perhaps manipulate these partial fractions to give me these standard forms. So if we take the first partial fraction, I'm trying to find the inverse Laplace of the 5 times s over the s squared plus 4 squared term. The a in this case would be 4. And if I take the 5 outside of the inverse Laplace transform function, I get s over s squared plus 4 squared, my s squared plus a squared. So I can see straight away I've got the standard form here for the cos of at. So I'm going to be able to write this term in terms of cos of at. That will be cos of 4t, because the a is 4 here, and don't forget I've got to multiply that by the 5. If I go to my second function, I'm looking for the inverse Laplace of, I've written this is 2 times 4, 2 times 4 is the 8. The reason I'm doing that is because I want an a over an a squared term, so I'm looking for my 4 over my 4 squared term, so the a in this case would be a. And again I get a standard form of the a over s squared plus a squared, so a in this case is 4. So I can write down my standard Laplace transform here as sine of 4t, sine of at, but again don't forget I have to multiply it by the factor of 2. So that's an example of how we take a non-standard inverse Laplace transform question, and we break it into partial fractions, and then we break it into standard form entities. Okay, example 3 here, we're looking for the inverse Laplace transform of s plus 8 over s squared plus 16s plus 113. Now if you look at the inverse Laplace transform table, you will see no transform that has a quadratic term on the bottom line, a quadratic expression in the form of ax squared plus bx plus c. So this is an example where we're going to use completing the square, and by doing this we'll be able to make the denominator into this format, the s minus a all squared plus omega squared type format. So so another sort of tool in our armory of being able to arrange non-standard inverse Laplace transform into a standard form. If you're not familiar with the completing the square method, I encourage you to look at a separate video purely about completing the square. Here I'm going to go through the 6 steps we usually use in the method. So the first step, I write down my denominator, in this case my s squared plus 16s plus 113 equals to 0. In the second step, I take the constant term, the 113, to the right hand side. In this case I subtract 113 from both sides of the equation, and that leaves me with the s squared plus 16s on the left hand side. Now I note the coefficient of the s term in this case is 16, and in this method for step 3 we half that coefficient value, so 16 divided by 2 gives me 8, and then we square it to get 64. So step 3 works out this constant 64, that in step 4 we add to both sides of the equation to keep the balance of the equations. I've added 64 to the left hand side and 64 to the right hand side. On the left hand side I can now factorise on the s squared plus 16s plus 64 in terms of s plus 8 squared. If you're not sure about factorising, I encourage you to go and look at factorisation, but we can factorise that as s plus 8 all squared, and on the right hand side I simply summate the values, so I get minus 49. In the final step, step 6, we bring the 49 to the left hand side of the equation by adding 49 to both sides, so I end up with s plus 8 all squared plus 49. Now that is in the form of s minus a squared plus the omega squared. So again, there's a little technique we can use when we have a quadratic in the bottom line to try and make it into a standard form. Okay, example 3 continued here. I've just repeated the inverse Laplace transform from the previous page for convenience. Now what we've got to notice here is that the top line of the inverse Laplace transform we're using is s minus a, but we have s plus a in our transform. So again, there's a little technique we use there to get the s minus a is we make our a term here in the brackets to be minus 8. So I now have the s minus a term, but the a is actually minus 8 in this case. So again, just be careful of that, the directed numbers I'm using there. Same thing on the bottom line here. We actually have an s minus a in the bracket in the denominator, and I've got an s plus a in my bracket. So once again, use the same technique. I'll put a minus 8 in a bracket. Don't forget the minus makes the plus there. So the a is minus 8, but I've now got my s minus a format in the bottom line. As for the omega squared term in the standard form, well, 49, the square root of 49 is 7, so I can write that as the plus 7 squared. So now I've got my format of the inverse Laplace transform of s minus a over s minus a all squared plus an omega squared. In this case, the a is minus 8 and the omega is 7. Now I can write my function into the time domain by taking the inverse Laplace. So I will get e to the at, where a is minus 8 in this case, and that's multiplied by cos of omega t, where the omega is 7. And there's my solution. Okay, final example, example 4. We're going to find the inverse Laplace transform of 2s minus 24 over s squared plus 16s. I'm going to try resolving this into partial fractions first of all, to write it as inverse Laplace of 2s over s squared plus 16s, and then take away 24 over s squared plus 16s, and see if that helps me. Looking at my standard Laplace transform tables, I can see that I have a 1 over s minus a. As we saw from the previous example, if I divide this term top and bottom by s, I will get a kind of format of 1 over s minus a that I can play with, so that might be useful. And if I look at the inverse Laplace transform table again, I'm going to try and use the omega over s minus a all squared minus omega squared with the second term. And again, this partly comes from experience. The more you do, the more you're familiar with the table, the more you kind of know what functions are likely to fit. But I'm basically trying these. If they don't work, I'll have to try something else. So I can write my inverse Laplace transform of the 2s minus 24 over s squared plus 16s as inverse Laplace transform of 2 times s for the first partial fraction over s squared plus 16s, and then take away the inverse Laplace transform of the 24 over the s squared plus 16s. Okay, example 4 continued here. Just repeated this line from the previous page. So I've got the inverse Laplace transform of 2 times s over s squared plus 16s for the first partial fraction, and I'm taking away from that the inverse Laplace transform of 24 over s squared plus 16s for my second partial fraction. Just going to focus on the first partial fraction first of all. What I'm going to do to try and make this into the inverse Laplace transform standard form is I'm going to divide the top and bottom by s. So dividing the 2s by s, I will get 2 times 1. On the denominator, dividing s squared by s, I will get s. And dividing the 16s by s, I will get the plus 16. Now to look at that in standard form, I need 1 upon s minus a as the standard form, so I need to take a 2 outside to leave myself with the 1 in the numerator. And my little trick here of making the 16 a negative in a bracket but having a negative outside still gives me s plus 16, but I've now written it in the form of s minus the a, where the a in this case will be negative 16. So now I can write down my inverse Laplace transform. So in the time domain we get e to the at, with a being minus 16 in this case, so e to the minus 16t, and don't forget to multiply by the 2 outside the function. If I return to the second partial fraction, for the denominator here, I'm going to use completing the square as shown in example 3. I'm not going to go through this in detail here, but that will give us 24 upon the s plus 8 squared minus 64. Okay. Now, that's not in the format I want. I need s minus a all squared minus omega squared. Now, the top and bottom here, the numerator value here and this value here must both be the same. They're both an omega, but the bottom line is an omega squared term. Now, in this case, 64, when you square root that, you get 8. So I can have 8 squared on the bottom, but to get my 8 on the top, I had to take a 3 outside here, because don't forget it's really 24 on the top. But by taking the 3 outside, I can still have my 24, 3 times 8 is 24, but I have my omega over the minus omega squared term here. So that's a little sort of trick as to how I managed to achieve that format. Again, inside the bracket here, I've got to have an s minus a term, all squared. Again, I do that by making the 8 a minus 8 in a bracket and have a minus outside. So again, I've still got s plus 8 inside the bracket, but it's written as s minus a minus 8 all squared. So in this case, my a is equal to minus 8, my omega is equal to positive 8. And when I come to write that into my function, I will get e to the at, as e to the minus 8t in this case, sine of 8t, sine of omega t there, which is 8t. Okay, don't forget again, we must multiply by that 3 outside, and the negative stays negative as it has all throughout the calculation. Exercise 3 is split into 4 parts for us. And there's some hints for each of the parts. Part A is actually in standard form, so look that up directly in your tables. Part B, I suggest you use completing the square on the denominator, and then look up in standard tables. Part C, resolve into partial fractions, and Part D, again, back to completing the square on the denominator. Answers are shown in the brackets. And finally, some tutorial questions for you to do. Again, the answers are shown in the brackets adjacent to the questions all the way through. I would encourage you to have a play with all these questions, and they're all based around the examples we've seen in the previous slides. Finally, some further questions for you to do. Again, the answers are shown on the sheet as you go through the questions. I hope this has been of some use to you. Thank you for viewing.